So there are different solutions, different kinds of waves and stuff, but the solution that we had been sort of working with is a plane wave solution. So you can think of this as a function of position and time that it looks like, sines or cosines or e to the j omega. And these are traveling waves, and you would have messed with this in the homework a little bit. There are some simple relationships, like, for example, that the speed of the wave, so I should say k is called the wave number. It's equal to 2 pi over lambda. Omega is simply the angular frequency, 2 pi f. Recognize that, k times x, suppose at t equals 0, there would be no term here, and then you would just have sine of kx. So at t equals 0. So you can think of this as, this is what you need to put in here has to be an angle. So the argument of the trig function has to be an angle. So in order for the units to work out, this has to be 2 pi over a length, so it's 2 pi over the lambda. You could do the same kind of thing with at x equals 0. Then there's no time piece, or sorry, then there's no spatial piece, and it would just be omega t. And then that's going to require you to be dividing by time in order for this to be an angle. And kind of the basic relationship between the wavelength and the frequency, which are buried inside k and omega, is that the wavelength times the frequency is equal to the speed. Since we're talking about electromagnetic waves, it's equal to the speed of light, at least in a vacuum. And something that's kind of cool about this is also when we looked at the wave equation, there was this fact that we could pull out the speed of light just based on mu naught and epsilon naught. So if you put in those constants that we've been working with this quarter, 1 divided by the square root of those, you will get the speed of light, which is kind of cool. That Maxwell's equations predict the speed of light. Something else I would mention about this quick, this stuff is in the videos that are posted too, but remember when we modified epsilon by adding a dielectric? Well, you can do the same thing in this context. If this becomes epsilon relative, where this is bigger than epsilon naught, or it's like some factor, like 5 times epsilon naught or something. What will happen is that would mean, since it's 1 over the square root of that, it will decrease the speed. So the speed of light in a material is less. And then kind of the only other, let's see, what else are you responsible for? Other relationships, like the speed of light, you can also express as the ratio between E and B. This is another way of saying that the magnetic field, in some sense, is weaker than the electric field. You could solve for B here, and you'd see that it's E over C. So that's why when we're normally talking about the electric interaction, the electromagnetic, we're long on the electromagnetic part of the electromagnetic waves, because it's kind of, you can think of it as being stronger. Let's see. Oh, and then kind of the other thing to mention in this last section is something called the Poynting vector. And this is what describes the direction of the wave propagation. So If I can draw this. If we think about this wave that has electric and magnetic components that are transverse to each other, perpendicular to each other, the direction of propagation of the wave will be perpendicular to both. So if you look at E cross B, so if you point your fingers up and bend them over into B, you would see that the direction of propagation for this would be in this direction. This is also the same direction as the velocity of the wave. And you should have seen this a little bit in the homework, but this is telling you how much energy per area. So these electromagnetic waves carry energy, and the Poynting vector is how you calculate how much energy. A lot of times it's not convenient to work with this, so I mentioned in the video too that you can re-express this in terms of E naught, where that's what we've been working with here, the magnitude. And so this would be the average value of the Poynting vector as opposed to the Poynting vector itself. So, and why one of the reasons that you work with the average rather than the Poynting vector itself is because the frequency of light is so large that a lot of times, I mean, you can't directly detect it. So this Poynting vector in general, this would be a function of time because E and B are functions of time. But if you look at like the frequency for visible light, so for example, remember we can just apply C is lambda over F. If you want to know what the frequency for visible light is, it's going to be uh-oh. Wait a second. Oh no. Sorry, technical difficulties here. I think my review document got messed up here. 1 second. Stand by. I accidentally like pasted another copy in here or something. All right, well, we'll just roll with it and see what happens here. So, if you were to solve for the frequency for visible light, you know it's going to be, come on, pen, the speed of light over the wavelength. So for visible light, this is, 3 times 10 to the 8th divided by, I don't know, 500 nanometers, 500 times 10 to the minus 9. Let's compute that. This is 6 times 10 to the 14. So this is 600 terahertz. There's no electronics or anything that can respond that fast. So you can't measure the Poynting vector. You can't measure the frequency of visible light directly. You can't measure the wave directly. So this is part of why we care more about the average value of the Poynting vector, i.e. the intensity. Anyway, that was basically the last little tidbit that we've talked about, and there's more detail on this in the posted video. So for those topics, you can look there. Are there any questions before we look at the review? Were there any of the questions in the review that you were in particular interested in? You guys there? Give me a thumbs up and we'll proceed then. All right. So while we're going through this, if there's something that you're that you want a clarification on, get me, shout it out, and we can pause and talk about this because this is probably the best thing in terms of messaging to you what will be on the final. So, all right. The first question here is just asking you, to use your Lorentz force and right-hand rule to figure out the direction of the force of a moving charge. So, remember this would be Q V cross B. So point your fingers in the direction of V. You'd bend them into the page because the magnetic field is pointed into the page, and you would find that your thumb, it would tell you that the force would point like this. So let me do this in another color. So the force would be like this. In this situation, Q V cross B, you point your fingers in the same direction and you orient them so that they're pointing along B. You would find that the force in this situation would be out of the page. If this were aligned along B, then you would have no force at all because the cross product would be 0 because they would be parallel. In other words, this if it was moving like this, no force. So you need to be familiar with those right-hand rules and how to calculate the direction of the force. This next question, we saw a question like this or scenario like this in the lab, and you also saw in either the group problems or we had practiced this, but this is definitely since this is such a sort of central scenario, I'm going to ask you something about something like this. So for this one, it's a little bit different in that now we're going to assume that the carbon is fully ionized. So we want to find the radius. And so we can set this up. If you sum the forces in the radial direction, so basically what's going to happen is this thing is going to, make a circle. If we sum the forces in the radial direction, that's equal to the mass times the centripetal acceleration, i.e. Newton's second law, but in a circular motion. And the force that we're working with is QV cross B, Lorentz force, and that's going to equal m. We can express this centripetal acceleration as v squared over r. V and B are perpendicular, so this just becomes QVB equals mv squared over r. We'll lose a factor of v, and then we can solve this for r. So r will be mv over qb. And we can put in our numbers here. The mass would be 12 times 1.67 times 10 to the minus 27. The velocity is 3% of the speed of light, so 0.03 times 3 times 10 to the 8th. The charge, now it's going to be 6 times 1.602 times 10 to the minus 19. We've lost all the electrons, so it'd be a positive 6. And then the B field was 2.5 Tesla. We put those numbers in, we turn the crank, you would find that this would be about 7.5 centimeters. So this would be the R for carbon 12. If you do this same calculation, but for carbon 14, notice this 12 would become, here, I'll just do it in a different color. So R for carbon 14, you would just pick up a factor of 14 instead of 12 there, and you would find since it's proportional to the mass, then this would be larger, which kind of makes sense. The force is the same, so it's going to make a smaller or a larger circle because it's more massive. And this is kind of the idea behind mass spectroscopy. If you had looked at the section in there about mass spec. So that's basically parts A and B. Part C, this isn't worded very well. It says if you were to apply 1 kilovolt across the plates, what would be the acceleration? What I intended to have here was if you were to turn off B. So regarding part C, turn off B. Basically, all I'm asking you to look at is what, if you're just talking about the electric force, you know that it's QE, and you know that this would be equal to the mass times the acceleration according to Newton's second law. So you could solve for the acceleration, would be QE over the mass. Just to remind us, refamiliarize ourselves with the electric part of the Lorentz force, if we're talking about both E and B fields being present. So this, and then you know that this electric field can be expressed as the the potential per distance. So this becomes Q V over D, and then there would be the factor of, we would be dividing by the factor of M. So this would be 6 times 1.602 times 1,000 volts divided by 0.055 meters divided by the mass, which is again 12 times. You crunch those numbers and you should find that the acceleration is 8.7 times 10 to the 11. So this is not dissimilar to when we did this sort of thing in the first lab. So if this is unfamiliar, refer back to the first lab. So that's part C. And then this last question, does the B field do work? It's kind of an interesting question. If you remember back to 2011, you know that work is F dot D, but the force and the displacement, when you're talking about a moving charge and the magnetic force, they're always perpendicular. You know, like, so in this situation, if the V is this way and the B is pointing into the page, then you know that the force is like this, but these are perpendicular. So by definition, F dot D is going to be 0 because the force and the displacement are in perpendicular directions. They're not aligned. So B field does no work. Okay. So that was that question. Questions on this guy? Can keep trucking here. This is a simple question on Hall probes. So recall a Hall probe was, you have like a piece of metal and you have a magnetic field that's going through the metal. What's going to happen is that if you run current through it, some of the electrons, some of the current is going to be accumulate on the edges of this because of the Lorentz force. You know, if you imagine a charge in here, it's going to feel a force that's perpendicular. And so you end up with a voltage, the Hall voltage, across on the opposite sides of this. And that Hall voltage is just equal to the drift velocity times the strength of the field times the width of the plate. So you don't actually need the width or any of this information to figure this question out. It's just mainly asking you to recall that the Hall voltage is proportional to the B field. So if the voltage goes from 3 to 4.5, that means that the B field has gone from 1 to 1.5 times whatever it was. Because it's proportional to B. Now, if it becomes negative, you've either flipped the probe around or the B field is now going in the other direction. So, room here. And you could see that, so now imagine that the B field's coming out of the page. The charge would be deflected in the opposite direction. You would get, negative of what you had before. So just a qualitative question. We didn't work a lot with that, but I want you to know, this. Let's see, magnetic fields around wires. So this is just another application of your right-hand rule. You know that if you point your thumb in the direction of the current and wrap your fingers around, that'll tell you the direction that the magnetic field is going. So for a wire like that, it would go like this. This one, you would be pointing your thumb at your face, and because it's coming out of the page, and you know that the magnetic field would be going around like that. More generally, you know that B equals mu naught I over 2 pi r, if you want to calculate the magnitude, which we'll use in a second here. Sketching the field for a couple wires. So in this situation, they're going into the board, so you would point your thumb into the page, and they're in the same direction. So B field for both of these would be like this. And then what you recognize is that in the middle, this one would be going like this. The other one, though, would be going like this. So in the middle, it's 0. They would cancel, provided that these are I1 and I2. If I1 equals I2, then in the middle, it would be 0. If the currents were not equal, then, that 0 point might be somewhere else. Alternatively, if they're going in the opposite direction, I guess all I'm saying is that you would also want to be able to analyze the situation like this, where now, one is going like this, but the other one would be going the opposite direction. Or, sorry, wait a second. The one that's going in would go like that. The one that's coming out would go like this. So now in the center, they would sum. And depending on the relative strengths, you might have a place where they cancel, but it wouldn't be between them. So, on variations of that. Question 5 is definitely the most difficult of all the questions. So I wanted to make sure that you had a solution to this one. Let's take a second and just see, do you guys have any questions so far?
3, what's the equation EH equals VDBD mean?
That's the Hall voltage. So that's for the Hall effect. So if I recall, this was in chapter 27. It's basically a variation on the, if you look at section 27.8, it talks about this. This is basically one of the more common tools that's used to detect and measure magnetic fields. You can think of this as like a B field measurement device. So like I said, it's not very complicated, and we didn't work with it much, but I would expect you to, have this expression. Good question. Other questions? Shall we proceed? How about you give me something in the chat, and we'll look at this question with the adding magnetic field vectors. So I'm definitely going to ask you something about something like this, because I think this is one of the more important skills. It's one of the more complex operations that you're asked to do mathematically, and I think it's a good thing because many of you may or all I'm trying to say is you may or may not be using like magnetic fields to calculate things, but these skills with vectors and more complicated scenarios, I think, is a good skill for you to have. So, all right, what's this going to look like? We know, based on what we were just doing, that magnetic field around a wire with these wires that are going into the board, both of them would look like this. So then at point A, you would have a contribution from this one that looks like this. And you would have a contribution from this one that looks like this. And what we really need to find is the result. That's what we're ultimately after, but we're going to break it down into pieces because it's sort of a complex problem. So those are the contributions. The magnitudes of these contributions. You know that the magnitude for a magnetic field around a wire looks like mu naught I over 2 pi r. So for these two situations, let me just label these like I1 and I2. The field due to I1 would look like, we need to know what this r is. So we would pick up a factor of the square root of 2 because this is d squared, square root of d squared plus d squared. So this would be mu naught I over 2 pi root 2 times d. The B field due to I2 is simpler because it's just a factor of d. I drew this one as longer because that's reflective of the fact that this is closer, so the B field due to I2 will be stronger. If we have the magnitudes of the two contributions, we need to sum the contributions in x and y. So I think the last question that we did that was like this, it didn't have contributions in both dimensions. This one does. So if we look at bx and by, let's do by first because it's simpler because it only has one piece. So by is just going to be, let me use a different color here to break down our contributions. By is just the component of the B field due to I1 that's pointing in the y direction. So by is going to be mu naught I 2 pi root 2 over root 2d times just, if we're looking at this, it would be just the sine component. So if this is theta, let's call this theta, times sine theta. Now these angles are set up so that since this is 45 degrees, and we know that this is perpendicular, this will be negative 45 degrees. So theta is going to be negative 45 degrees. And so we know that the value of that will be root 2 over 2. And it'll be negative, and that just reflects the fact that it's pointing down. So this would simplify a little bit. We just get 1/2 mu naught I over 2 pi d. Now the x piece is going to be a little bit more complicated. I can put that in a different color. How about? So the x pieces, we're going to have two contributions. There's this one. i.e. the component due to I1, and then there's also this one. So when we go to sum the x contributions, we're going to have one piece that looks very similar to what we just did, mu naught I, 2 pi, root 2t. Now it's even going to be the same because now this is the cosine piece, but it's cosine of 45 degrees, or negative 45 degrees. So this will also be root 2 over 2. Plus, we'll have the full contribution from I2 because it's all pointed in the x direction. So this will be plus mu naught I over 2 pi d. So if we add these together, we'll have a piece that's the same magnitude as the y piece. So 1/2 mu naught I over 2 pi d plus mu naught I over 2 pi d. And so, we have 1/2 plus 2/2, so we have 3/2 mu naught I over 2 pi d, and this would be the bx piece. So in other words, this piece would be in the I hat direction. This piece would be in the negative j hat direction. So that's x and y. Which is kind of the more complex step. And then to find the total, what would we do? We would add the contributions. So notice we have an x piece and a y piece. So the total would be like this. Now you can see much of this is the same. Let's call this factor just b prime. So this would be a factor of b prime squared plus 3b prime squared, just so we're not writing that whole thing over again. And so when you do that, then this becomes the square root of 10 times b prime. So in other words, the net magnitude of the net B field would be root 10 over 2 mu naught I over 2 pi d. And then to find the direction, make a little more room here. Sorry. For time. So we're getting close on time. So to find the direction, you can use the tangent. And this would be the tangent of by over bx. And when you do the arctangent of those two components, we have by and bx. You'd find that theta is around negative 18 degrees, which is reasonable considering our picture here. We know it's going to be less. It's going to be below the x-axis. So that's the magnitude and the direction. If we wanted to find, so we're kind of running short on time, so I will just tell you the solutions for the rest of the part. If we wanted to find the force, we know that the force due to a wire looks like IL cross B. Now these will be perpendicular because I is going to be parallel to the wires that are already there. So you would just multiply your B times a factor of I. So in other words, force per unit length would be I times B net. Let's see. So that's definitely the most complex question. So I wanted to make sure that you had a solution to that. This question is just asking us about Faraday's law in the context of a rail. And it says, we did one like this in class, so this is similar. If the current is going around like this, that would tell you that the magnetic field must be going like this. because it's trying to trying to maintain the magnetic flux, and that would tell you that the bar must be moving to the left because the area must be decreasing, and that current is set up in such a way as to resist that. So let's see. So given the magnetic field, you could find the velocity of the bar. So remember, this was the change in flux per time. So when we've solved problems like this before, but this will look like BLV. And so if you solve this for the velocity, you'd get I times R over BL. And if you put the numbers in, you'd find that this would be a speed of 5 meters per second. This question with the solenoid, we would want to write an expression for the magnetic flux. So the magnetic flux looks like the area times the B field. The area would just be pi r squared because it's a cylinder. The area of a slice through a cylinder. So it'd be, like a area like that. The magnetic field in a solenoid looks like mu naught I n per L. And so we have an expression where I is a function of time. So this becomes pi r squared mu naught n over L times I cosine omega t. So this would be an algebraic expression for the magnetic flux as a function of time. What I'm asking you for in the first part. And then to find the EMF, you know that this is equal to the derivative of the flux. And so you would take a derivative of this expression. Most of it is constant with respect to L, with respect to time. Except we would take a derivative of this cosine omega t. This would become negative sine omega t. And then we would pick up a factor of omega. And so if you put in all the numbers that are in here, the current, the frequency, and everything, you'll find that the max EMF is, what is the value? 1.3 millivolts. So you can think of this as being the expression that you get is basically going to be V naught times sine omega t, where this V naught is equal to 1.3 millivolts. And so that's the question about magnetic flux and the solenoid, etc. And then this last question is just a few things on Maxwell's equations. So if you had a cell phone that was at 800 megahertz, you could find the wavelength from C over F. And we did something like this, I think is posted in a video. And so this is like 37 centimeters. Part B. So the other thing that can cause a B field would be a changing electric flux. And then part C is just asking you to use the Poynting vector. So this is asking you to make use of 1/2 epsilon naught C E naught squared. If you put in, C and epsilon naught, you put in the numbers, you would find in this situation that this would be about 3 microwatts per meter cubed. So those are all the example problems. Sorry, it took a little bit longer to get through those than I had intended, but you have this as a resource for you as you study. And if you run into additional questions, don't be afraid to reach out to me if you have questions. So the other thing that I wanted to give us, we don't have enough time, I think, my thinking is that we would jump into the breakout rooms and look at these survey questions, but maybe we could just kind of have a discussion in the last few minutes, and maybe I'll post this as a survey, and if you have some ideas, I would love to get your feedback on these issues. So let's see. Can you see the document that I posted in the chat?
Did you just now post it, or is it from a while ago?
No, I posted it at the beginning, yeah. I can post it again as well. Here, 1 second.
Yeah, we can see it. You just gotta scroll up a while.
So just for sake of having it, oh, it won't let me post it again or something. You see it? So it's a Word document with a few questions, and I would love to get your input on some of these issues. So in addition to the class evaluations, so I know you've been, I think you've been being bugged in Canvas to answer those. Those are good, but they don't really give me, it's good, like it gives us general ideas, but I'd like to get a little bit more specific information. So since we didn't have as much time to devote to this as I had wanted in class, I can post this on Canvas as well. But in particular, the thing that I would love to talk about is basically the last couple questions on communication and on group work. So let's see. With regards to communications, how have you guys felt about communication for our class? Has it been at a reasonable level? Have you felt like you have too many different kinds of communication? Because this is a thing that faculty have been talking about that I would love to get some good ideas on. I know some folks are really feeling like they're kind of snowed in by too many different ways of communicating, emails and Canvas and Teams and everything. So what do you guys think? Why don't you talk? You can, just shout out what you think. I'm going to end the recording too here.
I think I like the fact that you kind of send out emails